Broadcast is now starting. All attendees are in listen-only mode.
All right, good afternoon, everyone. Welcome to our webinar entitled Performance of Thermal Shipping Systems Following Distribution, Part 1. My name is Tim Eels, and I'll be your moderator and webinar organizer today. Before we get started, let's take a moment to make sure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen, which you can minimize by using the orange button at the upper left. You can also expand it with the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We'll be answering a few questions today during the webinar. However, if we don't get to your question, someone will follow up with you after the webinar within a couple of days afterwards by email. And also, for those of you logged in right now, you can download a copy of the slide deck. So do that at any time so you can have it for good reference. So let's go ahead and get started. First, we're very, very fortunate to have two highly qualified presenters today. First, Edmund Tang. I want to introduce you to. He's a principal engineer here at WESTPAK. He's been with WESTPAK 19 years. He's also a director of packaging at San Jose State University, where he's been heavily involved in packaging for 14 years. Edmund has a bachelor's and master's degree in industrial systems engineering with a concentration in packaging, all from San Jose State University. Our second speaker, Mr. Eric Cardiel, is our production manager here at WESTPAK. He's been with us for at least 5 years. He oversees the entire production team here at San Jose and is responsible for all testing. He has a bachelor's in biomedical engineering from San Jose State University. And Eric's been very qualified as a test engineer before he got to the manager level. So we're very fortunate to have both Eric and Edmund giving this presentation today. Okay, well, with that, I'm going to turn it over to Edmund, and he'll begin the presentation.
Thanks for your patience.
All right, sorry about that. Little technical difficulties with regards to the mute and unmute button, but we should be good now. Apologies for those delays. And like Eric said, thank you for your patience. Here's a quick overview of our presentation today. First, we're going to talk about introduction, background, what this study is about, why we're doing it, and why we think that there might be a need for a change in the industry. Second, we're going to talk about the project scope and thesis, a little theory, and look a little bit about some standards that we think might need revising or just revisiting and just looking at it from a different angle. Talk about the testing conducted, what we did to validate, and just look at the evidence of our testing with regards to our thesis. And then we're going to present data and results, conclusions, and then following that, next steps for a possible next study or next presentation. All right, project scope and thesis. Let's do a little review here. So the test standard that we're looking at is ISTA 7E. But in general, it doesn't need to be a 7E standard. It could be any standard that is known as a thermal mapping standard. Thermal mapping standard is when you map your package and you validate your package through temperature, through some type of profile, and at the end of the day, you tell whether this profile is good for your package or your package is good for this profile to protect whatever's in there. So even though we state 7E, it could be used for any thermal mapping standard, theoretically. In case you're not familiar with thermal studies is a process of monitoring the internal temperature of products to evaluate how it performs according to a shipping profile. So with the 7E, we have summers, we have winters, and not limited 7Es, but then some of you know your own distribution environment. Some of you have mapped your own distribution environment. If that's the case, you can have a specific thermal study for that as well. But it's commonly used to validate cold chain shipments just because everything in there is super temperature sensitive. What does that mean when it's temperature sensitive? It means that if it's outside of the specified temperature range, then there could be a danger to the products, whatever's inside, whatever the final product is that the customer receives. And when we talk about thermal studies more in depth, where are they crucial to? What are they most important to? And we're going to say it's mostly crucial to the biotech industry. Yes, the biotech industry, the pharma industry. Most recently, it's kind of still in the forefront of our minds, but when we talked about the vaccine distribution for COVID-19, they had very, very strict requirements of it needed to be in this temperature range. If it was outside this temperature range for too long, then the efficacy of your vaccine might not be as potent as it could be. And then at this point, you're dealing with human lives, you're dealing with a vaccine that can potentially save your life or at least prevent a lot of headaches and pains in the long run if it isn't as crucial as if it isn't as strong and potent as it should be. So what are the shortcomings of 7E, or what are the shortcomings of any thermal mapping study in general? So the biggest shortcoming of these standards is that all shippers, they're all validated to best case scenarios. What is best case scenario? It means that these shippers are pristine. You get them in, you never drop them, you never do any vibration on them, you don't do any compression on them. Everything is best case scenario. It's packed out usually in a refrigerated chamber, and then it is ran through the profile. And at the end of the day, you say that based on the profile we saw and based on the results of your internal contents, it passes or it fails. But then if you introduce anything like a drop, vibration, then now you're challenging the shipper. Maybe if you're shipping with insulated EPS, the EPS will crack. When you do vibration, your products, your components, everything will get heated up just because of the energy associated with it. So the study is basically saying that there is an effect on your thermal studies with these physical tests, but let's find out how big of an effect it is. So this proposed study, as you could tell, is that we are still running a thermal mapping test, but at the same time, before a thermal mapping test, we have a whole bunch of cases, we have a whole bunch of scenarios. We're testing it through some test suites, some ISTA test suites, we're doing some drops, we're doing some vibrations, but either way, we're challenging the thermal shipper physically before it actually goes through the thermal portion of testing, because that is what it is. That's what represents a distribution environment. Never are you going to have a package that's never dropped, never vibrated, in perfect condition when shipped. That just doesn't happen. So this is our study to see what type of data comes out of it. And now we're going to pass it on to Eric for the next leg of this presentation.
Cool. Thank you, Edmund. So like Edmund mentioned, we were looking in the study, we're looking to assess the thermal performance of these insulated shippers, these packages, but also add in another element that we haven't seen before, the element of those potential transit hazards that could potentially affect the overall thermal performance of a certain package. So the way we did that was, obviously we had our control variable to compare against. We utilized ISTA 3A and 2A testing, and then varied pack out conditions, extreme conditions of those test inputs that were called out in the standards that we tested to, as well as some other fun stuff that we got into. So our test was set up in 3 different steps, right? We had our step 2, which are our variable conditions that I mentioned, that I'll get into a little bit more in detail in the next few slides. But step 1 was always the same, preconditioned and packed out at +5C for the same duration for all 9 variable test cases. And then after we went out and tested the shippers with all these variable cases, step 3 completed the study, the test with utilizing ISTA 7E, the summer profile for 72 hours, and monitoring inside that shipper to assess the thermal performance. Just some quick notes on the testing conducted. We did not use pre-validated shippers. The typical acceptance criteria is -1C to 8C, which is what we kept in mind for when we were assessing the thermal performance. Our payload was 8-ounce water bottles, 12 per shipper. The reported data was also an average of 4 data sets per variable case. And just for the sake of keeping our variable cases as controlled as we could, all test samples were exposed to lab ambient conditions after the preconditioning for 4 hours. So no matter what type of variable cases we were testing to, we made sure to limit the variability by keeping them outside of the chamber for 4 hours after test or during testing. And then, of course, like all testing done at WESTPAK, all our devices and instrumentation is maintained and calibrated per ISO 17025. Okay, so step 1, like I mentioned, we preconditioned our gel bricks to -20°C for 72 hours, as well as our payload shippers, or our payload at +5°C for 72 hours as well. Okay, so this is our first step here. So after that 72-hour preconditioning, we packed out at ambient conditions. Now, with the exception of variable case 9, where we actually packed out at ambient conditions to see if there's any difference. And there's me and Edmund freezing in the chamber, having fun there. Closed beer bottles, that was staged, I assure you. Okay, and here's an example of our shipper. So like I mentioned, the payload inside our payload shipper, which is a corrugated fiberboard shipper, surrounded by gel bricks, the gel packs that we preconditioned at -20°C, all encased within an insulated shipper, and then all within our outer shipper there, bleached corrugated fiberboard there. And then top-down view of our package system here. We have a 6-ounce cold bricks in the bottom layer. And our payload, we mapped the 2 innermost water bottles in each of the 9 variable cases. And then we surrounded by 12 and 8-ounce cold bricks, again, all preconditioned to -20°C. And then on top, we're, again, 5 more 6-ounce cold bricks. Okay, so step 2, variable case 1 was actually just no variability. So our control system, so just exposed to ambient conditions for 4 hours, and that was our baseline, just to compare the rest of our data to. All right, our second variable case was testing to ISTA 3A. ISTA 3A calls out testing to simulate the trans environment, which includes drop testing at 18 inches and 36 inches, as well as stacked vibration, which is, at least for here at WESTPAK, a kind of 2 tests in 1. So we have that dynamic compression testing, simulates, it's getting shipped in a truck or wherever, and we have packages stacked on top, seeing how that outer shipper performs. Okay, our variable case 3 was actually taking our 2 standards that we were referencing, ISTA 2A and 3A, and combining all the drops that they call out in those standards on our 2 shippers. So ISTA 2A calls out 10 drops at 38 inches. And then, like I mentioned, ISTA 3A has 2 separate drop sequences called out, detailed right here. Okay, and then between the 2 standards that we tested to, ISTA 2A actually has the most intense vibration profile compared to ISTA 3A as far as overall energy level. So we just ran that for as long as we could to make sure we still kept within that 4-hour ambient exposure time after preconditioning, and then just ran a bunch of vibration. So variable case 5, we actually combined the 2 cases that I mentioned previous of the extreme drops, so all the drops called out in ISTA 2A and 3A, as well as the vibration called out in ISTA 2A. And like I mentioned, ISTA 2A calls out compression testing, vibration without a top load, because we already do compression to start the test off, drops, and then ends with vibration, that intensity level that I mentioned previous as well. Okay, then we varied our actual package system conditions. Variable 7, we actually punctured gel bricks to see if potentially damaged refrigerant could affect the performance of our shippers. And we just took that flathead screwdriver, poked a couple holes, and assessed. And for variable case 9, we cut into the insulated, the EPS, cut at 4 vertical edges with a bandsaw to allow for extra airflow into the where the payload shipper was housed. Like I mentioned in a few slides ago, variable case 9, we packed out at ambient lab conditions. So instead of ideal cases, like we wanted to see, okay, if we're not packing out at plus 5C inside the chamber, how does that affect our performance? And we were trying to be as speedy as we could, 5-minute pack out time there. And then all those variable cases ended with the ICA 72-hour hot profile detailed here, as well as monitoring that performance, that internal temperature throughout. And we'll take a pause just for any questions anybody might have.
Thanks, Eric. And Edmund, thank you both for going through that material. You covered a lot. Had a couple of questions that have come in. First question had to do with the payload that you chose. Why did you use water bottles for the payload?
So the reason why we used water bottles, now hindsight's 2020, we realized that probably it wasn't the best decision. It was just readily available, and it was something that we could get nice and snug into that inner package that we have there. When we actually presented this in the ISTA conference, a few people mentioned that water bottles wasn't representative of the pharma industry, and we do realize that now, unfortunately. But for the study, unfortunately, we didn't have that knowledge before we tested, so we went with water bottles.
All right, cool. Another question. How many replicates of each variable were conducted?
That's a good question. Yeah, so for each variable case, we utilized 2 shippers, 2 similar package systems, and then we also monitored 2 water bottles out of those 12 internally, so 2 locations for each shipper, so a total of 4 data sets per each variable.
All right, thank you. Let's go ahead and resume our webinar. Edmund, I think you're up next.
Okay, let's look at the results here. So before we talk about results, let's talk about acceptance criteria. So based on the pharma industry, we do realize that typical storage conditions are +2 to +8 degrees C. If you look at just what we pulled up from the FDA website as well, we have the COVID-19 vaccine, Moderna, it says right there in red, +2 to +8 degrees C. However, for this study, just because, like Eric said, we weren't using a pre-validated package, we had to broaden the range of what it passed to. So we went as low as, -1 degree C we deemed acceptable, because when we packed out everything, that was the lowest that the lowest temperature got. So we modified the bottom, but we still kept the top portion of the +8 degrees C. So that said, let's look at the combined data. We're gonna look at all these one by one, each graph by itself, based on, I would say, based on the variable. But right now, I'm just going to show everything combined. So don't worry about not being able to see the individual graphs or charts, because that's not the intention of this slide here. So let's look at the one with have the lowest effect. So we went from minimum all the way to what we call extreme effect. And this is just an ambient pack out versus the controlled pack out. So this is when Eric said that the controlled pack out is we're packing out at +5 degrees C, which is the temperature of the water bottles. And then what happens if you don't pack it on plus 5 degrees C and you pack it out in an ambient lab plus 23 degrees C? What is the difference? And we actually have values for the deltas now, but right now it's just showing you a visual representation. So you compare the control, you compare the ambient, and you look at, yeah, that is not much of a difference here. There's not much of a gap there, not that too big of a delta. Next variable here is ISTA2A, ISTA3A, extreme vibe, and cut edges. So with these variables, we have what is known as a minor effect. So you can see that there's a little more pull away than the ambient pack out one, but still not that much more, but the big gap is bigger. So again, we're going to give values to each of these lines later on, but right now it's just a visual representation, just so everyone could see it visually and just a little easier to say the least. Punctured gel bricks. So this is when we went and stabbed all these gel bricks and made holes in it, and they had a pretty good effect. So what can punctured gel bricks simulate? It could simulate, for instance, you get your gel bricks from your supplier, and they're not all perfect, and you think to yourself, oh, it's not perfect, but if we freeze them, will it be okay? Well, you can see now that if you use all punctured gel bricks, which hopefully you're not using, there is going to be a good amount of pull away from your control. Extreme drops. This is when we subjected the package to ISTA 2A and 3A drops. So 2A has 10 drops, 3A has 16 drops, so a total of 26 drops. So a lot of drops on this package, major effect here. You can see that pull away with the graphs. And then finally, we have what is known as extreme drops and extreme vibration. And this just logically would be the biggest delta, simply because we have the most test inputs and we beat this shipper up the most. But there it is visually, where you have the control and extreme drops and vibration. Now that we've seen everything graphically, let's talk about everything in a sense that we can actually put some numbers on it. So control testing, case scenario, shipper for thermal mapping and shipper thermal validations. So at this point, it failed. It exceeded plus 8 degrees C at 59 hours and 20 minutes. And then the next column here, we have the delta from the control. So this is the control, so there's no delta, and therefore there's a 0% degradation. Degradation is how much faster did the variable fail compared to the control. So right here, pack out in ambient conditions, as we remember here, it's instead of packing out at plus 5, we packed out at an ambient lab. And it only failed 35 minutes earlier. And if you take that ratio, take that percentage, it's a 1% degradation. So not too bad, as long as you're packing out fast and you're not packing out too many. And the next set is what we call the moderate or minor, is that we have extreme vibe, ISTA 2A, 3A, and the cut insulated shipper edges. Surprisingly, this was a big surprise for all of us. We thought there would be a bigger amount of degradation. We thought there would be a bigger pull away, but we're still short by an hour 15 to an hour 25. At the end of the day, it's not that much. Percentage-wise, it's around 2%, but the data is there, and we honestly thought it'd be more. Punctured gel bricks, we categorize this as the next category, and this one failed almost 2 hours before. 2 hours before, take a percentage, 3.2% degradation. It failed a little faster, but quite honestly, not that much faster than what we expected. And then finally, we have the most extreme case of we take the shipper, we're beating it up, ISTA 2A, ISTA 3A, seeing all the drops, all the vibration, and it failed at 5 hours before the control shipper. And with this degradation, we have a 8.3% degradation. So if you think about this in, I would say, the distribution, this is the difference between shipping a FedEx first overnight, where you have that really, really early delivery versus just a FedEx anytime overnight, where you might have that late delivery. So that is the data in number format with the degradation and how much earlier it failed at. Okay, so let's go with conclusions and recommendations. So in conclusion, the distribution environment I would say, you know, 2A and 3A is pretty good representation of distribution environment. Surprisingly, it was only degraded by 2 to 4%, which wasn't what we expected. We expected a bit more than that when packed out in the refrigerated chamber. And then also, if it's packed out in ambient conditions and not in the refrigerated chamber, you have another 1 or 2% degradation, which honestly isn't that much either. But then if the shipper experiences some type of irregular, extreme dynamic inputs during distribution, like some crazy drops, then it could deteriorate by 4 to 14%. And although we're not talking about days, we're talking about hours, but that's the difference between the early AM delivery versus the anytime delivery for next day. And what do we recommend? So recommendation is that, you know, what's the cost of failure? What's the cost of going out of tolerances? When we're talking about vaccines, when we're talking about anything pharma, biomedical, it's always better to be safe than sorry. So if you have a 3-day pack out and you're shipping a 2-day, then you're in good hands. But if you have a 3-day pack and you're shipping out 3-day service, then you might have to reconsider the same thing. So just be careful when you're riding that line of trying to have the optimal package, but at the same time, wanting to have the best quality when you deliver your product. Because when you introduce a distribution environment to anything, especially thermal shippers, there's going to be some degradation. So you definitely should have some type of safety margin with regards to that, because the tolerance for failure for these types of products should be 0 or close to none. All right. Next steps. So what do we want to do next? So one of the big things that we didn't do is that we didn't combine variables. Well, what does that mean? That means that we cut the edges for the insulated shipper, but that was it. We didn't do cut edges plus drops, cut edges plus vibration. And same thing with the ambient packout. I'm curious about the ambient packout. Ambient packout plus distribution. What does that look like? Even though ambient packout was 1% and distribution was another 2%, I'm guessing it's not a linear relationship where you could just go 1 plus 2 is equal to 3. I'm guessing it might degrade maybe 5 or 6, but at the same time, we don't know. So the next thing that we really want to do is that we want to combine variables, and we also want to think about new variables. And I think we have a break now for Tim to ask any more questions from the audience.
Thanks, Edmund. You covered a lot of detail, and I know there was a ton of work that went behind gathering that data. A couple of questions came in. One of them had to do, again, about the payload. How do you think the data would change if you did not use the water bottles for payload?
All right, water bottles again, the crux of this study here. So as mentioned before, hindsight's 2020. We definitely got a good amount of questions with regards to this payload when we presented at ISTA. And the main reason why is because water bottles, if you think about it, they hold a lot of thermal mass. And if they hold a lot of thermal mass, then the package is going to look better than it is. So before I answer that question, what should we have used? We should have used vials, very, very small vials that would represent vaccines. They wouldn't hold too much thermal mass, so therefore it would represent what is out in the real world better. So if you would ask me, what if we didn't use water bottles, and what if we used like a real payload that represents the distribution environment, like a vial, I think these results wouldn't be as good, just because the water holds that refrigerator temperature quite a bit. And we would see, I would say, bigger pull-aways and a lot bigger degradations with regards to the package. Unfortunately, this is the data we have, so this is what we're presenting. But good questions, and we wish we did it better, or we wish we used a real payload.
Thanks, Edmund. Another question had to do with future continuation of the study and future work. What do you have planned?
Yeah, I can take that one. Yeah, I mean, we definitely continued the study and want to keep adding on to this, and definitely checking out, different variable cases, right? Like different types of inputs a particular shipper could see in the transit environment. just orientation of the shipper matter, using different refrigerant like dry ice. A lot of pharmaceuticals are shipped in that type of package system. Varying our payloads like Edmund mentioned, and then combining variables. I'm actually very curious about that. I know Edmund mentioned it, but that's also one that is very. I'm curious about that.
Okay, well, Edmund and Eric, I want to thank you for the presentation today. One of the references that we have for you, and this is the ISTA 7E protocol is a very extensive and expensive protocol, but you can get a kind of an overview of it free. All you got to do is go to the IST website. We've got the URL though for you. It's a PDF download. I think it's about a 12-page document. It's a fraction of the 7A in its entirety, but it gives you a good overview of that protocol, which is essential. Also, I wanted to give you the URL for our cold chain test services webpage on our website. There's a lot of good information there, and that's where you can find it. Also, if you've got questions, or if you'd like to get some information on our testing or get a quote, there are several ways you can reach us. And this slide shows you some of the more popular ways. You can click on our URL for our request a quote form, and you can fill out your contact info and some basic details on what you're looking for. You can also call us. We've got a 800 number there for you. And also you can go to our portal, whether you're an existing customer or not. You can go to our portal and communicate with us through the portal. And finally, we have an info@WESTPAK email address. You can use that as well. This slide gives you a quick overview of some of WESTPAK's test capabilities and industries that we test for. WESTPAK has been around a long time. We specialize in package testing, but we've got experience in all these other areas as well. So hopefully we can help you if you're not already one of our existing customers. And finally, a little bit about WESTPAK. WESTPAK is a third-party independent test laboratory, and we specialize in mechanical and environmental testing. We currently have 2 California-based testing laboratories, one in San Jose and one in San Diego, California. Both labs are ISTA certified, and the testing that we perform is accredited ISO 17025. We began operations in 1986, and in 2017, we became 100% employee-owned. So everybody that you've heard from today is a part owner of WESTPAK, and all of our nearly 100 employees are actually owners. Finally, by email, within a few minutes, you should be receiving a 1-question survey. And we're simply going to ask you if you've got other webinar topics that you'd like us to address that would be helpful for you. Please let us know what those are. And again, thank you all for attending today. Thank you for your questions as well. I'm Tim Eels, your moderator. Make it a great day.